Okay, welcome to Chapter 3, 3.1 Exponential Functions. This should be perhaps your second look at these. For some of you, maybe you haven't dealt with exponential functions, but basically an exponential function is just when we have a variable in an exponent for the most part. And in this case, where a is greater than 0, we want to have a positive value here, but a is not equal to 1. And because if a was 1, it would just be 1 to the 5th, 1 to the 6th. We would have a constant solution of just 1 here. So that's an exponential function. And we'll talk about the formulas for compound interest and why maybe they make sense. Continuous compounding, that's going to be one that you're probably going to need to commit to memory. But we'll make sense out of that first compounding problem when we get to that. So let's start with graphs, and I'm going to approach this as though you have never seen a graph of these before, and we're going to just graph f of x equals 10 to the x. So we're going to start with a t-chart until we have a good feel for what our parent function looks like on exponential functions. So if I were to choose values for x and plot them, we've got it. I want to choose values that make my exponent become 0. So in this case, I would say 0 is a great choice to start for x, whereas if we have a problem like this later on, I might want to build around x equals -4 to make the exponent 0. So if I put in 0, I get out 10 to the 0th, which is equal to 1. So 0 gives me 1. And you note, for every function, for every exponential function, if it was just plain old a number to the x, that point would be on there. If this was 7 to the x, 7 to the 0th, 1. If this was 1/3 to the x, 1/3 to the 0th is 1. I'll refer to that point as a pivot point. And of course, it can move around, but not if it's just a plain old base to x. We'd have to have a shift to the right or left, or make it twice as tall, or shift it up or down. Okay, then when x is 1, of course, we get 10 to the 1st, or 10. When x is 2, we get 10 to the 2nd, or 100. How about when we put in -1? 10 to the -1st, we should recall, is 1 on 10 to the 1st, or 1 on 10. And likewise, 10 to the -2nd is 1 on 10 to the 2nd, is 1 on 100. So if we were graphing this, and we could rescale, but I already called this 0, 1. By the time I get to 1, I'm already up to 10. So what do we have? 7. So we're somewhere right up in here. When I go to -1, I'm down at 1/10. -2, I'm at 1/100th, 1/1000th, 1/10,000th. I'm going to get closer and closer and closer to 0 very quickly, but I'm not going to, that's terrible, but I'm not going to ever cross it. And therefore, based on last section, we should realize what we have there is a horizontal asymptote of y equals 0. We're also supposed to identify any intercepts. Well, I don't have an x-intercept. The graph I'm going to claim is entirely above the x-axis, but I do have a y-intercept of 1. In this case, our pivot point. Okay, and that's the gist of it. So we might expect some things to be a little different here. Like obviously we don't have a base 10, but maybe our graph's going to look sort of like that graph, and it's backwards, and we're just not dealing with as big of numbers. But I'm still going to just t-chart this for now and say if x is 0, then I get 3/2 to the -0, which is 3/2 to the 0, or 1. Same pivot point. When I put in 1, I get 3/2 to the -1st, or 2/3. 1 gets me 2/3. When I put in 2, I get 3/2 to the -2nd, or 2 on 3, but squared, 4/9. And third, I get 3/2 to the -3rd, and I get 2 on 3, but to the 3rd, 8 on 27, which is, a little bit more than a third, or a little bit less than a third, isn't it? A little bit less than a third. So I think it becomes clear here, once again, we're just getting sucked into 0. We have a horizontal asymptote. Try that again. Horizontal asymptote of y equals 0. Let's move backwards now When I put in -1, it just flips the fraction. Or, excuse me, I'm sorry, I get 3 halves to the positive first, 3 halves to the positive first, 3 halves. When I put in -2, I get 3 halves to the positive second, 3 halves to the positive second, 9/4, or 2 1/4. When I put in -3, I get 3 halves to the positive third, or 3 to the third, 27, on 2 to the third, 8. And if you notice, we're just getting reciprocals here of one another. This is a terrible 27. So that is about 3.5. So we're just ballparking. And we start getting a feel for what this graph looks like. And for accuracy's sake, we can put more in, but we're pretty comfortable it feels like that. We do not have an x-intercept, and that is it. Okay, library of parent functions. So I'm going to just jump down and take a look at these. We got some graphs. This one's going down where our previous ones went up. There may be some, well, I guess we had a downward one here where our previous ones went up. This one's going up, but it looks like it has a horizontal asymptote that's up 1. This one looks like it has a horizontal asymptote that's perhaps down 4. This one looks like maybe, because we're typically going through this point, maybe it's one that looked like this and it's shifted to the right a little bit. So let's take a look there. Sorry if I had those out of view. Up 1, down 4, pivot point normally right here. Maybe that got shifted to the right. So I'm going to start with this one. Do we have an equation that looks like maybe it would be shifted up 1 from what we were used to seeing on numbers 10 and 16? This looks just like 2 to the x, except it's up 1. This graph should look just like 2 to the x, which I'm claiming should look something like this, except it's backwards. If I flip it over backwards, I believe that one's A. This graph looks like it's down 4. There's a down 4, C. And this graph looks like perhaps it shifted to the right, but it still has that y equals 0. Looks just like this, only it's shifted to the right. And I believe that one is D. Okay, parent functions. This is along kind of the same lines. Use the graphs of f and g to describe g. Then sketch them by hand. Okay. So we're going to go through the descriptions of these right now because we're doing some other graphing. So I'm going to toss that part out of the assignment for this, assuming we can do that by the time we've gotten through some of the earlier problems here. So the graph of this would look just like the graph of this, except we have a pre-function addition. Therefore, our most interesting value of x, what I refer to as MyVox, most interesting value of x is -4, which implies a shift to the left 4. Now we have 10 to the x up above, so if you want to graph them both by hand, we got 10 to the x up above. We had it looking something like this. Our graph would just look just like that, except it would be to the left 4. Okay. You can work on that, but again, for the assignment purposes, I'm just looking for what our translation is. So 0.3 to the x, not exactly certain what it looks like, but here we're -0.3 to the x plus 5. But this is a post-function negative. This negative is not getting squared, or is not being raised to the x power. It's 0.3 to the x. Then we turn that y value, we turn that pre-function, or that function, into the opposite. That's upside down and up 5. So we just say upside down and up 5. And this is truthfully, it's tough to see here. This is a negative. I'm a little fuzzy here, sorry about that. The graph of this looks just like the graph of that, but first we have a pre-function addition, so it is left 4, and a pre-function multiplier by -1. We're making time go backwards before we let it be the exponent on 1/2. So that is backwards. Now maybe the better way of describing that mathematically would be to say it's a reflection over the y-axis. Like this point would reflect over to there. But it's just backwards. What used to be forward now is backwards. Likewise, upside down, what used to be up here is now down there. Upside down, maybe the better way of saying is that's a reflection over the x-axis. Okay, 2024, same thing. The graph of -2 to the x would look, or the graph of g, excuse me, already includes that, but has a +5. So that is just an up 5. This graph includes 2 to the x, except the most interesting value of x is -2, so we are left -2, and then post function subtract down 3. We're just left 2, I'm sorry. Left 2 units. We have a horizontal translation of -2, but it's left 2 units, and then we're down 3. Again, that goes back to what we talked about back in chapter 2, the beginning, and some of the most important stuff that we're going to deal with all, I guess that was chapter 1, excuse me, some of the most important stuff we're going to deal with all semester. Okay, not the friendliest, and probably for test purposes, not crazy about graphing in terms of E. E for our practical purposes is about 2.7. When we're graphing, that's about as accurate as we're going to be able to possibly try to illustrate, and that might even be a stretch. So the graph of e to the x, if I was just graphing e to the x, when I put in 0, I'd get out 1. When I put in 1, I would get out 2.7. When I would put in -1, I would get 1 over 2.7, and we start getting a feel. When I put in 2, I'd obviously get whatever 2.7-ish to the second is. That's going to be 7, 8, somewhere in there. So it's going to be it's still going to look like our parent function. Okay, now, maybe the most important thing I notice here at the start, besides the shift to the left 1, maybe the most important thing is I realize it's a shift up 2. If this graph shifts up 2, the asymptote shifts up 2. And then I can go ahead and maybe try to get some decent t-chart values. Let's choose values of x, figure out what y would become. I would start with -1. That is most definitely the most friendly value of x. Because when I put in -1, I get e to the 0th, 1, plus 2, 3. -1, 3. And that's really where my pivot point moved to. Notice my pivot point usually starts here. It went left 1, up 2. And now when I put in 0, I get e to the first, which is about 2.7, plus the 2, we'd be at about 4.7. So up 1, 2, 3, 4.7. And when I put in +1, I would be e to the second, 2.7 plus 2. I'd be off the chart by then. When I put in -2, I would get e to the negative first, about 1 on 2.7 plus 2. But I'm always going to be a little bit above 2. So this is about a third plus 2. It's going to be somewhere in here. But we've got it. We've got enough information. And again, we might want calculator if we were going to go for any more detail there. So let's see, sketch the graph of the function, identify the asymptote of the graph. The horizontal asymptote was pretty easy to identify. This graph looks just like e to the x, except it's left 1. That doesn't affect the horizontal, but up 2. Y equals 2. Okay, number 54. Here we're going to go ahead and go graphing calculator, which I have not preloaded this function. And we're to graph this thing. So let's see here if I can get a good zoom in on this. Let's go here where we can see a little bit of both. I need a compromise. There we go. And lock that one in. Not the greatest. One more try here. All right, I'm going to just have you trust me that I've got that I'm typing in the correct function here. So I've got 8 divided by quantity 1 plus second ln is e to the, so e to the negative 0.5 divided by x. And I'm just going to zoom standard that thing, so I'm just going to go straight to graph on this. So there's our graph, and all appearances are that 0 is an asymptote, that x equals 0 is an asymptote, and maybe somewhere around 4. For instance, if I go second calc value, I'm just going to jump out to say 9. And there we are, a little bit above 4. I'm going to jump back to negative 9. And there we are, maybe closing in on 4, getting up. So it seems maybe 4 is reasonable. How about if I put in just 0? Oop, graph doesn't exist there, so we do have a vertical asymptote there. I'm going to go to window because they suggest that. If I go to table, we note 0 doesn't exist, and here we're getting the values are starting to get a little bit smaller. Kind of interesting there for a bit, but as we move on, we start becoming believers. You know what? Maybe 4 is an asymptote. So let's go ahead and take a look away from the graph here. Let's go back to here. Let's see if that makes sense. First off, is there a problem when x is 0? Well, you bet there is, because x is in a denominator right here. So it appears like maybe we have a vertical asymptote at x equals 0. That causes some problems for us. We thought the horizontal was 4. So let's think about this. As x gets bigger and bigger and bigger, I get e to the negative 0.5 over, say, a trillion, which is basically e to the 0th, which is basically 1. So it's pretty much 8 over 1 plus just about 1. It's pretty much 8 over 2, whether it's positive, negative there. So yeah, it does make sense that we would end up approaching 4. So horizontal asymptote, y equals 4. And again, we're just to graph this on our calculator. So the table's kind of helpful there. You can track down the table pretty quickly. We can see what those values approach. I don't know if that views well, but I'm not going to reformat. We can see that we're approaching 4. Okay, number 58. Use a graphing calculator to find the points of intersection, if any, of the graphs of the functions. Round your results to 3 decimal places. So once again, I'm just going to ask you, bear with me and realize that I am going to be graphing these two functions as y1 and y2. But I want you to get a good look at those. So y1, we're going to have, let's clear that out. And let's go 100. Second ln is e to the. We'll talk about why that is, why they use that function for it. And I want 0.01x. And my second function is just plain old 12,500. And we're looking for the intersection of those. So if I go straight to graph and I just graph it in standard, we're not going to probably like too much what we see. So if we think about this one for a second, if I put in 0, this graph is already up at e to the 0th 1. This graph starts up at 100. This graph is up at 12,500. It would make sense to me that we want to do some adjusting there. So I'm going to change my y window to at least include 12,500. I think I'm going to take it up to maybe 15,000. So I'm going to go back here, and I'm going to go to window. I'm going to have my y max be 15,000 now. And I think I'm probably interested in when as x gets bigger and bigger. I don't know how far out I'm going to go. I'm just going to go to 100. I'm not putting much thought into this right now. So x max 100, y max 15,000. Let's graph that. So there's our first function. And the blue one down here, I don't even know if you saw it graph, but it started looking like it's growing. And of course, this one's going to stay flat. So I've got to go quite a bit bigger here. So I'm going to go window. Let's go to, say, 10,000. Now we see, wow, that blue one eventually grew really, really fast, and it's still trying to graph it. It's just off the chart. There's our intersection. So if I just trace this thing, let's get back over to where we get close to 0. We see that right here I'm at 445, and then it jumps over our 12,000 mark right away. If you want a better look at this, maybe we just want to go to, say, 700 or so. So I could go back to window. I'm going to go to X max of 700 and graph that. So what we learned there, hopefully, is that, man, these exponential functions, when they get committed, they really take off. And now we can second calc intersect. First curve, the first curve we're on is the exponential e to the, get close to the intersection, enter. Second curve, get close to it, enter. And yes, and our intersection occurs at 482.831. Use the graph to find points of intersection, so that was 482.831, and of course it's at 12,500. There's our intersection. Round your results to 3 decimal places. Okay, pretty simple, but an important tool for us, particularly in like a chemistry environment. Okay, approximating relative extrema. That's mins and maxes. So here we've got another function we're going to graph. And I'm going to ask you to trust me that I'm going to just graph this function. So you can see what's going on here. We'll resume this one, or reset our window. Y equals, clear out that one, and clear out this one. I want x to the third, step out of that, second e to the, that second ln, negative x plus 2. That is a very, very common calculus type equation. They're real world equations that could model. So I'm going to go back to Zoom 6, good starting place, Zoom standard. And let's see if we've got anything in there. Well, that's a pretty interesting graph. Looks like we've got that x cubed, and that kind of makes sense. It should look like a cubic around 0. And then we've got an exponential kind of taken over, so a lot going on there. If you understand, this is pretty crazy to think about. This x cubed in here is doing its thing, but then the e to the negative x plus 2 must be taking charge and bringing it back down. Let's take a look at this. So our graph, I'm not going to spend a whole lot of time trying to make this really, really accurate. Our graph has a global representation that looks something like that. And my point being, hey, this x cubed, we know that thing grows fast. For x cubed, you know, our plain old x cubed graph looks like this, and it's represented right around 0 really well. But by the time I put 10 in here, we're already at 1,000. But e to the negative 8 is going to start to become really, really big. If I put negative 10 in, this is going to become 1 over e to a big positive, and this thing is going to get close and close to 0. So we have the battle of wills between this trying to become a big number as x gets big, and this trying to become a little number as x gets big, a number close to 0. Well, it's clear to me this is more powerful over the long run than that, because our solution is getting close to 0. Okay, so what are we supposed to do then? Use a graphing calculator to graph the function. Use the graph to find the open intervals on which the function is increasing or decreasing. So this function is increasing, appears from negative infinity till we get to whatever that point is. Negative infinity to that x value. It's decreasing, appears like, you know, maybe we need to explore more, but I believe it's going to keep getting sucked into 0 here. Appears like it's decreasing from that point until infinity. So I guess we will need to find something out about that point. So let's go second calc max, left of the max, right of the max, enter, and the x, wow, it appears like it's probably 3. Increasing until we get over to 3, decreasing, I believe, from 3 to infinity. If you're not certain on that, you can expand the x window, and I think you'll convince yourself. Okay, and approximate any relative max or mins. Well, that is a max, and it looks like it's 9.933. So we have a maximum at 3 of 9. What did I say that was? 9.933. And I think that's it. I think our minimum, this is going to go down forever. I believe this is going to get pulled into 0 closer and closer. And again, you can explore on your calculator if you want to see that. Okay, got some zooming issues here. Complete the table to determine the balance A for $2,500 invested at a rate R for T years and N and compounded N times per year. So back to the front page. Our compoundings per year is this formula. In class, I'm going to explain why that formula should make some sense, and we maybe can remember it because it makes sense. This is one for continuous compounding that we probably should memorize. And get this thing locked in here. Okay, so when n equals 1, our formula for compounding is going to be the amount we end up with equals principal times 1 plus the rate we're getting divided by the number of times it's compounded per year raised to the number of times it's compounded per year times the number of years. That's the formula from the front page that we'll use for each of those. For continuous compounding, its amount equals PE to the RT. So I'm just going to do as an example 4. So for 4, we would have our amount equals our principal is going to be $2,500 times 1 plus our rate is going to be 6%. That's 0.06. But here's the deal. We don't get all of that 6% 4 times a year. We only get 1/4 of it. But we get it 4 times a year. So how many times do we get it? 10 years times 4 times a year. And then that is most clearly a calculator problem. So let's see, maybe we're in good enough shape that we can see both right now. I don't know if that's probably a little bit too bright. Let's see if I can do this. I don't think my brightness is diminishing much. There we go. Should have thought of that before. So maybe we can see everything here. Let's go quit. Let's just go 2,500 times 1 plus 0.06 divided by 4 raised to the 10 times 4, and we end up with $435.05. $4,535, yikes, and 5 cents. And then the nice thing about this is, if we're going to go back and change the number of compoundings, like let's see, so I'm going to say this is A4. I'm going to go A12. All I need is 2,500, 1 plus 0.06 on 12. That's the bad news. Our rate is reduced. We get only 1/12 of 6%. The good news is we get it 10 times 12 times. So if we hit second entry down in the bottom right-hand corner, I get that formula. Now I just need to turn this thing carefully into 12. Let's see, I need to insert, divide by 12, and I need to change my 4 to 12 here. And let's see how much difference it makes if the bankers figure out our interest every month instead of just 4 times a year. And here we end up with a little bit more money, which is maybe what we would expect. 45, 48, 49. And so we'd have A12, A4. I'm going to leave A1, A2, A3, 65 for you. But then continuous compounding has its own formula, and that's a formula that we use in, not really for money, but in chemistry quite a bit. It would be the amount equals the amount we started with, the principal, 2,500, e to the, ooh, boy, I'm having some issues writing, e to the rate 0.06 times time, 10 years. So let's find that one. And we should get a little bit more than the monthly, because that's like every instant they're recalculating my interest. So I'm going to go 2,500 second ln e to the 0.06 times 10. And sure enough, 45, 55, 30. And the more it's compounded, the more often it's compounded, the more we should get. All right, and finally 69 to 72. Complete the table to determine the balance A for $12,000 invested at a rate R. So here we're going to let the number of time, the number of years we invest. And this is your economics lesson of the day. The good news with time is in the exponent. So the longer, and the exponent is called the power for a reason, the longer we leave things in, it can become dramatically different. Now, if you are only getting a rate of 2.5%, historically that wouldn't be so good. That might have been good a couple years ago, but historically on investments, you could almost bank, on a decent, solid, stock market investment, mutual fund or something, you may be able to bank on 6+%. There were actually times when the banks were paying that. So I'm going to just jump to, I think I'll do 10 and I'll do 50 years. So this is compounded continuously. So this is A equals PE to the RT. So I'll call it A with 10 years is we invested $12,000 E to the 0.025 times the 10. And we get, I'll clear this mess, and we get 12,000, second ln, there's our E to the 0.025 times 10. And we end up with $15,408.31. And now if we take that same investment, second enter's right down here, very bottom corner, second enter, and just edit this guy, and we go 50 years, and we enter that, we see we get $41,000. So the same amount of money invested, just given more time to go to work for you, a 50 is 41,884.12. And that's your economic lessons. Like, when are you going to start investing for retirement or maybe your children's education? You can start when they're, their education. Maybe you can start when they're 8 and have that investment out there for 10 years before they're going to college. Or when you get your first job, maybe you don't have children for 10 years after. Now you got that 20-year time frame. If you could start your investment and planning then, it's remarkable what a difference trying to control. See, what you want to control most, you can have some control over how much you invest. And you don't have too much control over the rate, but you definitely have control over the time, and the time is critical because that's part of the exponent. Obviously, how much you invest makes a difference, but the time is the critical thing, and that's the one that escapes most people. Is they're like, oh my gosh, I'm 58 years old and I'm looking at retiring, and how am I going to be able to do this? Well, you're 58. You should have started thinking about this when you were 22. Highly recommend you give some thought to that. So here's our assignment for 3-1. Some pretty good real world type problems in there in the economics area. They'll have some nice little chemistry problems coming up in this section, chemistry type problems, which I think for those of you in chemistry, you may get a little bit of a different appreciation for the mathematics behind it. As always, come in with questions if you have them, and good luck. See you soon.